Okay, so when I look at my first thought is, oh, I see a quadratic and I see a linear, maybe I can do a U substitution. Right, when I try the U substitution, it's the obvious choice is I'm going to choose the 2x squared minus 7x. I might as well throw the plus 3 in there because it'll disappear anyway. And then my du becomes a 4x minus 7 dx. But I don't think I can make a 4x minus 7 into an x minus 13. Okay? If I could just multiply it by a single number or divide something out, obviously to make the x's match, I'd have to divide by 4. But if I divided by 4, I'd get a minus 7 fourths, not a minus 13. Okay? And so there's not just a simple multiplication or division that I could do to make this work. So U substitution is out, right? It'd be nice if that was some multiple of 4x minus 7, but it's always interesting to me how subtle the differences need to be, where one thing will work simply by U substitution and you change the number just a little bit and it doesn't. So what we need to do on this one is look at this and say, okay, I've got a linear over a quadratic. This is a rational function. It looks like maybe somebody had two smaller rational functions that they had to add or subtract together, and maybe this was the common denominator that they came up with, and this is what happened after they adjusted the numerators accordingly. And this would be much easier if this was then written as a 1 over or something over a linear function plus or minus something else over a linear function. Because if it's just a linear function, then my U substitutions absolutely will work. If it's just a number over a linear. Okay? Because those can only differ by a multiplication of a constant. So the question is, if this is the result of finding a common denominator, then I must have had two linear things that I multiplied together. So if I want to know what those were, I need to factor this. And clearly I'm going to have a 2x and an x. I'm going to show you the factoring with the area model. So if this thing is going to factor, then the 2x squared is going to come from there, and the 3 is going to come from there. All right? And the interesting thing about this is, well, I know that these two things have to add up to negative 7. All right? So these have to add up to negative 7x on that diagonal. I also know what they have to multiply together to get. Because these two things will multiply to give me exactly the same thing as when I multiply these two together. So when I multiply them together, they have to give me a 6x squared. When I add them, they have to give me a negative 7x. So the question is, what do I multiply together to get 6, but add to get negative 7? Now, it's got to be a negative 6 and a negative 1. And so I'll put the negative 6 into one of these and the negative 1 into the other, and it doesn't matter which one. As I then go through and I pull the greatest common factor out of this, which is 2x. But if that's a 2x, then that must have been an x, and this must have been a negative 1, and that must have been a minus 3. So this factors to a 2x minus 1 and an x minus 3. Take some of the guesswork out of factoring. All right, so what did this look like then? I'm guessing that it looked like something where there was a 2x minus 1 in the denominator, plus an x minus 3 in the denominator. And there was some number up here and there was some number up there. And I assume that it was just a number because if it had an x in it, then there could have been some long division that was done and changed into something that didn't have an x in it. Okay, so in its simplified version, it would have to be a constant over the linear, so that the degree is smaller in the numerator than the denominator. And we said that if that was what happened, then somebody had found the common denominator here, right, and multiplied these things together, and they ended up with that. So let's do that. Let's take this and find the common denominator, which we know is going to be 2x minus 1 times x minus 3. And we would have had to adjust this numerator by multiplying it by x minus 3. So that would have been a times an x minus 3. The b would have had to have been multiplied by 2x minus 1. And so what we get looks like ax minus 3a plus 2bx minus b over 2x minus 1 times x minus 3. In this, when they simplified it, they got x minus 13 in the numerator. So this has to be the same thing as I started with, the x minus 13 over the 2x minus 1 times x minus 3. And the only way that these two things are going to be equal to each other is if the numerators are the same. Right? Because the denominators are already the same. So, can we figure out what the a and b were? Well, we can split this up a little bit. I could group the pieces together that have x's in it. I have an a plus 2b. Those are the pieces that had x's in them. And I had a negative 3a minus b. Those are the pieces that didn't have x's in them. And that has to equal x minus 3. 13. Thank you. Thoughts? Insights? Would you believe me if I told you that a plus 2b has to equal 1? Okay, you see that? Because the a plus 2b over here is the coefficient of the x. Coefficient of the x on this side is a 1. And so what equals negative 13? Negative 3a minus b. Or I could say 3a plus b equals positive 13, get rid of all the negativity that doesn't belong in calculus. So. Okay, how does that help? It's a system of linear equations. So, how do you want to solve it? Are you going to do substitution or elimination?
Multiply the bottom by 2.
Multiply the bottom by 2? Okay. Do you mind if I multiply by negative 2?
Yeah, that's
okay. So negative 6a minus 2b equals negative 26. And then I had this a plus 2b equals 1. And if I add those together, negative 5a is equal to negative 25. So a must be 5. And if a is 5, well, then I know 5 plus 2b has to equal 1. So 2b has to equal negative 4, and b must be negative 2. which means I have now translated my problem into the following problem. Okay. I had a over 2x minus 1, so 5 over 2x minus 1, plus negative 2 over x minus 3 dx. And that's a much easier problem to do. Okay. Let's see, this is going to involve a natural log of 2x minus 1. It would be the 5 from there, and the chain rule would kick out a 2, so I would need a 5 halves in front of that. Okay with that?
That's the absolute value of it.
Yeah, it should be absolute value. Plus or minus 2 times the absolute value of x minus 3 plus constant. Two times the natural log of the absolute value of x minus 3 plus constant. How much time do we have left?
It's not important. I think that was so easy.
Well, it took up quite a bit of space.
Yeah, but I'd mess up on there at least once or twice.
Is that generally the feeling like there were so many steps in there that something's going to go awry? Let's see if we can do something about that. This is the way that I learned to do it. How I did it through college, and then I came across the first textbook that I taught calculus out of here, and the guy had a trick. And of course I didn't trust the trick at all because it seemed like it made it way too easy. Eventually I came up with, and it actually was helped by this book. I think this book calls it the Heaviside method. And it's going to stem, he kicked it off right in here. I'm just going to start it from scratch. So let me grab this problem. And then add a page here. Okay. We're still going to have to start out with factor. Okay? And so we're going to rewrite this problem as indefinite integral of x minus 13 over 2x minus 1 times x minus 3 dx. Okay. Now, the way he described it in the book, okay, is why I call it the old give it the finger method. Okay. You take your finger, which I'm going to represent with my whole hand here, and you look at this first thing down here and you ask, what number would I have to put into that to make that equal 0? 1 half. Okay? Now I'm going to cover this up, and I'm going to replace all of the remaining x's with a 1 half. Okay? So that would give me a 1 half minus 13 over 1 half minus 3. Half minus 13 is negative 12 and a half. 26, negative 25 halves. Half minus 6 halves is negative 5 halves. Negative, negative, positive, flip over, 25 halves times 2/5, cancel, equals 5. That's the A.
That's 10 times easy. Then you just do it for the other one?
Yep. So for the other one, we ask ourselves, what would I put in there to make that 0? That's a 3. So now I cover that one up, and I get a 3 minus 13 over 2 times 3 minus 1. 3 minus 13 is negative 10. 6 minus 1 is 5. That's a negative 2. So this is plus a negative 2 over x minus 3. I don't often teach shortcuts, but this is such a good shortcut. Okay?
And why do all that extra work when you can do that much work?
Because you love algebra.
Okay.
You like showing off your solving systems of linear equation skills. All right, and then from there, we can go from there, right? Okay.